So now we have our 1 over 2 pi. Now, the first exponential integral, of course, the integral of an exponential just gives me my exponential back again. So I'll have e to the power, and I noticed everything is multiplying here k. So I've got a minus epsilon minus iu multiplying k. And then the nice thing about integrating an exponential like this is what you get is your exponential back again, but then divided by whatever is multiplying your integration variable. So divided by this constant, minus epsilon minus iu. And this then, of course, is evaluated between my limits going from 0 up to infinity. For my next term, once again, I will combine my exponentials. Again, I've got a common factor of k, so it's k. And now it's multiplying instead epsilon minus I times u. And then, once again, when I integrate such a function, I guess I've been writing more the k on the far end. It doesn't really matter, but I'll just try to be consistent here. When you integrate, of course, then you have to divide by the factor that is multiplying your integration variable. So that gives us epsilon minus iu in this case. And now my limits go from minus infinity to infinity. So then we can continue in our analysis. Our job next is to insert the limits of integration. When we insert infinity, we'll have infinity. Now this iuk part will be oscillating, but notice the infinity for k will multiply a minus epsilon. So I get a decaying exponential out at infinity. That, of course, gives me a value of 0. And then I can subtract, and when I insert 0 for k, I get e to the 0, and that, of course, evaluates just to 1. And then I have my denominator down here, minus epsilon minus I times u. Plus then, for my next term, the limit when I stick in 0 for k, I get e to the 0, which again is 1, and then I subtract off. Now when I put minus infinity for k, I have a minus of a very large number multiplying this positive epsilon. So again, I get an exponential decay. There may be some oscillations, but I get this exponential decay, e to the minus infinity times epsilon. That would give me 0. And then in my denominator, I have epsilon minus I times u. And that completes my expression. Now we can simplify a bit. The zeros, of course, can go away. They don't do anything for us. The signs here work out nicely. I'll just multiply through by a complete minus sign. And so now you see I have a sum of two fractions. And naturally, we want to put these on a common denominator. When I multiply these two to get my common denominator, it looks like one of these a squared minus b squared type expressions. So I'll have epsilon squared minus I times u quantity squared. But the trick is that when I do I times u quantity squared, of course, that just evaluates to minus u squared, because squaring I, of course, gives me minus 1. This is a parentheses. I'm sorry, right? So then iu quantity squared is minus u squared. So it's actually a plus sign on the bottom. On top, then, you know how this goes, right? I'll have this factor divided by the product to produce that 1. So then I'll have epsilon minus iu for my first fraction. And my second fraction then has this numerator on top of the two factors. So that would be epsilon plus iu. And we see we have another very nice cancellation between these u terms. So all I have then is 2 epsilon on top. So at the end of the day, I've got 1 over pi instead of 1 over 2 pi, an epsilon on top, and then an epsilon squared plus u squared in my denominator, and that is my final evaluation for this function m of u. Very nice. So we've got now our function. We need to think a little bit about what this function actually looks like and how it behaves so that we can use it, remember, in the large integral expression that we're working on, which is up several panels up above us. So if I were to make a plot of this m of u, it has some very interesting features. So here's m of u as a function of u. The first thing to notice is that whether u is positive or negative, it enters as the square in my denominator. So as u gets larger, this function is always decaying away, right? The maximum of this actually must be at the origin at 0. So it has a certain maximum, and then it decays down from there. And that maximum value we can evaluate when u equals 0. I've got epsilon over epsilon squared, gives me a 1 over epsilon. So this is 1 over pi epsilon. Now remember, epsilon is some super tiny quantity. So the maximum of this function is actually going to be heading towards infinity as we take our limit where epsilon is very small. So that's kind of unusual. The next thing to think about is, what if u has some sort of normal value, something significantly larger than the super tiny epsilon? Well, in that case, the epsilon squared plus u squared could be well approximated by just u squared, and then I will have just epsilon divided by u squared. But if u is some normal type number, epsilon over it is going to be, again, a very tiny number like epsilon. So for any decent sized u, right, my function is going to be essentially 0 out here. Now the only exception to this is when u gets small enough so that it starts to become comparable to epsilon. And when u actually equals epsilon, plus or minus, so here would be plus epsilon, here would be minus epsilon, those points give me a very interesting value, because that would then give me epsilon over epsilon squared plus epsilon squared. That's epsilon over twice epsilon squared. That's exactly 1/2 the value I had when I had stuck in 0. So at exactly half the height of this peak, I will have 1 over 2 pi epsilon. And so I have a very narrow peak that decays essentially to 0 outside of a range. It hits its half value at epsilon, but outside of the range from minus epsilon to epsilon, this is a essentially 0 function. So I have this function that as epsilon gets larger, right, it's growing up towards infinity, while at the same time, as epsilon gets smaller, it grows to infinity, while at the same time as epsilon gets smaller, the function is actually shrinking down, so that in some kind of a limit, as I take the limit of this epsilon goes to 0, what I get is a super infinite, very large function, but only over a very tiny range of values. Now that should start to remind us of something, right? That should really begin to look like, this is as epsilon becomes smaller than any physically relevant scale. That should begin to remind us a whole lot of something like a Dirac delta distribution. In fact, it's acting just like a Dirac delta distribution. The only thing we really need to check on here is whether or not it actually is a distribution. In other words, that it integrates up to something like a unit probability. So I need to check now whether or not 1 equals the integral of m of u du. Right? If that does hold, integral du m of u, integrating, of course, over all possible values, we need to check this, right? If it works, then we know then that this would imply that, in fact, m of u is acting exactly like one of these delta distributions. So let's see, actually, if we can conclude that. Well, I have to integrate m. So we have our function m up here. Right? So I integrate this du. So there's a 1 over pi on the outside. I have integral du, and my function m is epsilon, remember, over epsilon squared plus u squared. Now, this looks definitely like something that is crying out for some kind of change of variables. I want to pull out some kind of scale factor on u. It looks like I want to make like u equals v times epsilon or something, right? And then I'll be able to combine these epsilon terms. That looks very promising. Now, mathematically, a quick way we can see what the change of variables should be would be if we were to take our numerator and our denominator, and I'm just going to divide them by epsilon squared, because you can see how this would just work out nicely for a change in variables, because then I would have 1 over pi, integral from minus infinity to infinity. Here I have du over epsilon, so I'll have du over epsilon. And then the other pieces are 1 over epsilon squared is 1 plus u squared over epsilon squared is just u over epsilon quantity squared. So now you can see this is definitely crying out for this quantity to be called v. And if I call that quantity v in a change of variables, then this here is very clearly dv. So I have 1 over pi. And of course, we don't know this is true yet, right? We are just checking this. But what I do know for sure is m of u is this integral that I've been evaluating. So I've got 1 over pi. Now to update, no, I don't want an update right now.